Hi guys. So in our last video, we talked about classifying matter, which means you're looking at an example of matter and deciding if it's an element, compound, homogeneous, or heterogeneous mixture. Now we're going to take it another step further and also be able to determine the phase of matter. So whether it's an element, compound, or a mixture is besides the point. We want to know now if it's a solid, a liquid, or a gas. Um, so you can kind of look at the particle diagrams that I have here at the top of the slide, and we're going to just go through this data table and like check off the properties that apply to each. So let's look at a solid first. So the shape of that solid in that container is a cube, right? And I like to think of water as an example. Let's say I drop an ice cube into a beaker. The ice cube has a square shape and the beaker is a cylinder. When I drop that square shape into that cylinder, does it change its shape or does it stay a cube? It's going to keep its own shape. So the way we describe shape and volume for phases of matter is we say if they're definite or indefinite. So because solids have their own shape and it doesn't matter what container they're in, we say that solids have definite shapes. Okay. And volume is going to be definite also. If I measure the volume of that ice cube and then I put it into a beaker that's bigger than that ice cube, the size of the ice cube doesn't change. It has a certain size, and that size doesn't depend on what container it's in. As far as if it can be compressed or not, that means like, can you take the molecules in the sample and can you push them closer together? So take a look at this particle diagram. Does it look like there's space to push these particles closer together? No. So we say that solids cannot be compressed. As far as particle behavior goes, I want to show you guys an animation. So this is just an animation, and we're going to look at all of the phases of matter. And this is an example of something in the solid phase. So particle behavior is like what the particles are doing. So you can see they're kind of like wiggling around, but they're staying in their same position. They're not really moving to different spots. They're wiggling in their own space. They're also very close together. They're very organized. They're very neat. And as far as like how fast they're moving compared to the liquid and the gas phase, they're not moving very fast. They don't have a lot of energy. They're staying in the same spot. So if we go back and look at our chart for particle behavior, we can say that they're in a fixed position. Realizing I didn't leave you guys a lot of space. They're in a fixed position. They kind of vibrate in place. And energy, we could say, is low. Now, IMFs, this is an abbreviation for intermolecular forces. And we're going to talk in more detail about intermolecular forces in a couple units from now. But in a nutshell, intermolecular forces is how attracted particles are to each other. So you want to think about how close they are. If things are attracted to one another, they're going to get really close. Where if things are not attracted to one another, they're going to be far apart. So take a look at my solid and look how close together they are. That means that those molecules are very attracted to each other, which means that they have strong intermolecular forces. Okay. Now, if I look at my liquid, guys, for liquid, if I take a liquid that's in a cylinder, in a beaker, right, and I pour it into a flask, how is the shape of the liquid going to change? Now it's going to be in the shape of a flask. So for shape, it depends on the container that it's in. So the shape is going to be indefinite. Volume is still definite. if I have 50 milliliters of water, whether it's in a cylinder, beaker, or a flask, there's going to be 50 milliliters of water in both things. Okay. As far as can it be compressed go, the answer is also no. There's a little bit more space between liquids than solids, but you can look, they're still very, very close together, and you can't push them any closer together. So that's no. For particle behavior, so let's go back to our animation, and this time we'll look at something in the liquid phase. So you want to think, how is the behavior different than what we saw in the solid? So the particles are not staying in the same spot. They're still not moving super fast, but they're moving faster and more than in a solid. And now they're kind of sliding. We say they slide past one another. They don't stay in the same spot. So can slide past one another. Because the particles are a little bit further apart than in the solid phase, that means that they're not as attracted to each other as the solid phase. So the IMFs are moderate. And we could say that the energy is also moderate. The particles have more energy than in the solid phase, but they don't have a ton of energy in the liquid phase. Okay, now we get to a gas. And if you look at the particle diagram, notice that the gas spreads out to take up the entire shape and volume of the container. If I took those same gas particles and I put them into a balloon, the shape of the gas would now be a sphere. And the volume of the gas would be whatever the volume of the balloon is. So for the gas, both shape and volume depend on the container. The gas will take up the whole volume and be that shape. Can it be compressed? Yes. Think about taking a balloon and squeezing it together. There's room in between those particles to make them get closer together. For particle behavior, if I look at the gas phase, so now you can see, guys, our particles are moving much faster and they're much more random than they were in the solid or in the liquid phase. So for particle behavior, we can say they are very random in motion. Because they're so far apart, we know that the attractive forces are weak. That's why they're not getting close together. They're not very attracted to each other. And for energy, we can say high. Okay. Now down here, I have the abbreviation AQ, which we talked about in our last video, means aqueous. It's not really a phase of matter, but it describes a solid dissolved in a liquid. So if you had to pick, let me just finish writing, in a liquid, in water, really. It should be water. So aqueous really helps us classify the matter. We know that it's a homogeneous mixture if we see aqueous, but if we needed to pick a phase that aqueous would be most like as far as behavior goes, it would be like the liquid phase. Okay. All right, so let's talk about, now that we talked about phases, we want to talk about mixtures and how we can separate them. And in a lot of cases, the phase matters. So because mixtures are different things just physically combined, they can be physically separated. For example, if I have oil and water, because they're already in two separate layers, I can just like pour the oil out. So it's not like as complicated as doing a chemical reaction. So the three techniques for separation of a mixture are listed here. We're going to talk about filtration first. Filtration only works when you have a solid and a liquid. So we have something like sand and water, okay? And if we look at a diagram, filtration, it's almost like if you think of straining spaghetti. You have spaghetti and water, and when you're getting ready to eat the spaghetti, you dump it through a strainer. The water comes through the holes and the spaghetti stays in the strainer. So this is a funnel, and there's filter paper inside of this funnel. And the solid is going to get stuck up here, and the liquid is going to end up coming through and ending up in our beaker. So we can separate a mixture made up of solid and liquid using filtration. So why does this work? It depends on, you can say because you have a solid and a liquid, but you also might see the wording different particle size. So basically, like if we had sand and water, the sand particles are too big to pass through the filter paper, so they don't. And the water particles are smaller, so they're able to get through the holes in the filter paper and come through. Okay, chromatography is our next example or way to separate a mixture, and this works when you have two or more liquids mixed together, but they have similar boiling points. And we'll get to that in a minute. For right now, I'm just going to show you how chromatography works. And basically why it works is because the different liquids, they have different solubilities in water. Some of the liquids are more soluble in water than others. Okay, so here's another fun little animation we're going to watch. Chromatography. So here I have a candy that's made up of blue dye, and I'm going to dissolve that candy in water. So now we have multiple liquids dissolved in water. Okay, I'm going to take my sample and I'm going to put it on chromatography paper. And now here are some other samples. So when my blue dot separates, I want to see what pigments make it up. So these are like the pigments that I'm going to compare it to. So now I put my paper in water. The water seeps up. Look at that blue dot separating. 1, 2. So there were 2 different pigments in that dye. Dye C and the unknown dye. So see how some pigments curl up the paper faster than others? So that has to do with how soluble it is. The one that went really high up is more soluble in water than the one that didn't go as far. So they have different solubilities in water. And another way you can word that is they have different molecular polarities. And right now you don't really know what that means. But if you see it, know that it means they have different solubilities in water. It means the same thing for now. All right. Finally, we have distillation. So the examples here are alcohol and water. So again, I have 2 liquids mixed together, or NaCl aqueous. So distillation can work when I have 2 liquids, or it can work when I have a solid that's dissolved in water, because if it's dissolved, filter paper can't separate it. Now, what's different here is that the substances have different boiling points. So if I heat up the mixture, the thing with the lower boiling point is going to turn into a gas and it's going to leave, and the other thing's going to stay. So here is a nice animation of distillation. So this is salt water, right? If you guys look at the particle diagram, the blue circles are water, the purple ones are salt. So if we play this, notice what happens to the water as we heat it up. It leaves, it turns into a gas, it evaporates. It goes through this is called a condenser. It's basically an area that's cold. So it takes our gaseous water and it turns it back into a liquid and drops it into this other container. So we're using the fact that they have different boiling points to separate them. Okay. So what other type of matter can we separate and how? We can always separate mixtures. We can also separate compounds, but we wouldn't be able to do that physically. We would have to do it chemically. Do you guys remember the only type of matter that can't be separated or broken down? Elements. because they're already in the simplest form. Okay, so here are just some diagrams for you to have in your notes, guys. Paper chromatography to remind you the thing that crawls the furthest up is going to be the most soluble, and the further down they are, the least soluble they were. And here's your distillation apparatus, and it shows us heating up. This is the mixture here. And then whatever was dissolved in the water is left in that flask, and we end up with just the water down here. And this is the part that cools the water off. Okay, so I think that's going to be enough for today, and we'll get more into the properties of matter in our next video. Thanks, guys.